Name's Jond. Bames Jond. Now tell me, my nerdy weapons specialist friend, what are we here to do today?
Today's mission is to break into Bill Engineering and see what information they have on thermodynamics.
Okay, and what weapons do I have to defend me on this trip?
You have this 6-shooter Nerf gun, and for communication, talk to Big Boss, Mr. D, you have this communication. Just click the top of the pin, it'll get you to talk to her.
Okay, and is there anyone I need to look out for on this trip?
Okay, you see the guys over there?
Yeah.
The one in the blue, he's the bad boss. The one in the on the right side with the camouflage jacket, he's the henchman.
Let's see.
Alright, this is the secret entrance down here. Your girl, Mrs. R, right here will let you in. Good luck. This is as far as I'll go.
Thank you. Mrs. D, I've got some important information here on gas. It says a gas is one of the 4 classical states of matter. It can be a pure substance like neon or a mixture of substances like air. It's distinguished from liquids and solids by the vast separation of particles. Because they're difficult to observe with the senses, they're described through the use of 4 physical properties: pressure, volume, number of particles, which are grouped into moles, and temperature. Gases also have extremely low density and viscosity compared to liquids and solids, and the particles of a gas are influenced more by pressure and temperature. Gases are also compressible, therefore, like solids and liquids, and their particles spread out or diffuse in order to evenly distribute themselves throughout any container. What do you make of that, Mrs. D?
So, Bames, what you're telling me then is that gas is a state of matter where the particles do not take on a definite shape and have no definite volume. So some examples would include the air we breathe and steam. Thanks, Bames.
You're right on, Mrs. D. This paper says that there's someone else working on something up in the chemical engineering lounge. We're going to go check that out.
Hey Nell, we have some pretty good information here. In thermodynamics, vapor pressure is a quantity description of the usefulness of a vapor to do mechanical work. The quality of a fluid is the percentage of mass that is vapor. Saturated vapor has a quality of 100%, and saturated liquid has a quality of 0%. For instance, in analysis of the Rankine cycle, the quality of a multi-phase working fluid would be understood to imply this definition. So, quality is calculated by dividing the mass of the vapor by the mass of the entire mixture. The higher the quality, the more work that can be produced from the vapor, and the less moisture to cover the part.
Alright, so you're telling me, Ms. R, that the quality represents the percent of the total mass that is actually vapor, while saturated vapor quality is 100% and saturated liquid quality is 0%. And you're telling me the equation is the vapor mass divided by the liquid mass plus the vapor mass. Alright, Mr. R, got that down.
Hey Pops, there's another professor working on something in the civil engineering lounge. Let's go and find out what it is.
Okay, let's do it. Dude, haven't we already killed you twice?
Huh? No, I don't think so. I think I'd remember if I had been killed twice, thank you.
Yeah, I guess so.
No, I don't think so.
Mrs. D, it looks like we got some more information here on kinetic energy. It says that the energy of motion of certain masses is kinetic energy, and it's equal to 1/2 mv squared. Having gained this energy, a mass will retain it unless some non-conservative work like friction or air resistance causes a decrease in speed. And the amount of work required to reduce the kinetic energy to 0 is equal to the amount of kinetic energy that the mass originally had. Also, since velocity is frame dependent, so is kinetic energy. So if we were moving alongside a bullet at the same speed it was traveling at, it would appear to have no velocity and thus no kinetic energy. It can also pass from one object to another through a collision. So what do you make of this?
Okay, let's see if I got this straight, Banks. Kinetic energy is basically the energy a certain mass has due to its velocity, equal to the work that was done on the mass to get it to that speed, and is dependence on reference frame. Sounds good,
All right,
Banks?
sounds like you've got it, Mrs. D. According to this, someone else was working on another project in the industrial engineering lab, so we're going to head that way now. That's that same guy.
Yeah.
Get out there. Get out there. Right now.
Hey nerd, we have some information about the second law of Thermo. State that no process is possible whose sole result is the transfer of heat from a body of lower temperature to a body of higher temperature. This kind of process is possible only if work is input. An example of that would be a refrigerator, where the source of work is the compressor. This law adds another restriction to what machines are possible because it also tells us that the entropy generated by a process must be greater or equal to zero. In the case of a reversible process, the maximum amount of work is produced and there will be no entropy generated. However, a machine where the entropy generated is negative is impossible, like a perpetual motion device.
All right, Mrs. R, so what you're saying is the S-gen is greater than or equal to 0, and perpetual motion devices are not possible because entropy generated is negative. Okay? And the second law of Thermo states that no process is possible whose sole result is the transfer of heat from a body of lower temperature to a body of higher temperature. Okay.
Hey nerd, sounds like you get it. But it doesn't really say where we're going next.
Where the last piece of information at?
I don't have it.
Where's the last piece of information at?
All right, I'll give it to you. I'll give it to you.
I have it.
I need you to read it off my friend for me.
It's on heat capacity. Heat capacity is a physical quantity that represents the amount of heat and energy required to change a body's temperature by a given amount. Derivations include molar and specific heat capacity. Molar heat capacity is energy over moles times the change in temperature. Specific heat capacity is energy over mass times the change in temperature. It is a measurable intensive quantity that is different for every substance. Heat capacity represents the constant pressure heat capacity, while CV represents the constant volume heat capacity. They're related by the equation Cp equals Cv plus a constant R. In the case for an ideal gas, delta H equals the integral of Cp dt, and delta U, the integral of Cv dt. You got this?
All right then, heat capacity allows us to calculate the amount of energy required to cause a certain change in temperature if we know how much of a substance we want to heat up and what temperature difference we want to cause. Judging by the units, we could use the equation delta U equals mCp delta T, or something similar.
Sounds like you've got it, Mrs. D.